All right. Well, thank you. So we've talked a bit about self-paced exercise today. So I'd like to delve a bit deeper into this area, which is very controversial. So it'll be interesting to see if some of the questions are at the end. But it's obviously, as has been demonstrated by any of the talks today, aerobic performance or prolonged aerobic performance in the heat is impaired and can sometimes even lead to heat-related illnesses. Now, the performance impairment has been observed in both constant rate exercise as well as self-paced exercise. And obviously the difference between the two is that athletes can't regulate pace during constant rate exercise because the work rate is fixed, whereas during self-paced exercise they can self-select, depending on the test in the laboratory, either the cadence, which changes the power output, or depending on the ergometer, also the gearing to pace how they want to. Now, during constant rate exercise, this is a classic study that's been shown, I think, once or twice already today. But in terms of temperature, 11 degrees, even 4 and 21 degrees are enhanced time to exhaustion compared to 31 degrees when exercising at 70% of VO2 max. And during self-paced exercise, one of the first studies by Tatterson in 2000 examining 23 degrees and 32 degrees, we can see that in cool conditions, power output is maintained from the onset of exercise. Then we have the end spurt, whereas in the heat, it progressively decreases, flattens out, and then again, there's an end spurt at the end. And this end spurt is common to self-paced exercise in the lab anyways, where the subjects are informed of the end point of exercise. Now, this is not observed only in the lab, but also in field conditions. This is during a run, so in cool conditions. 13 degrees WBGT compared to 27, you can see speed or running velocity starts similarly, then decreases in the heat, and then that end spurt again. And again, we've seen this, I think, 3 times today, so marathon times increase as the WBGT increases. Now, if we look at self-paced exercise itself, it's obviously very multifactorial, unlike constant rate exercise where you just have to focus on pushing the pedals. Self-paced exercise brings different factors into play. So, for example, the athlete's objectives, their goals, their knowledge of the task, which is obviously very important. If you're going to do a 5-kilometer time trial, or if you're going to do a 55-kilometer time trial, then that will affect how you pace. Prior experience, current fitness level, as well as ability. Environmental conditions, if you're doing this outside as well, course geography, if it's a hilly course, if it's windy, things like that. And obviously sensory feedback and neural feedback during the effort. Now, bearing this in mind, pacing during self-paced exercise, yeah, that makes sense, is obviously a conscious behavioral response that comes into play in order to manage effort. And there's been many recent publications or reviews regarding self-paced exercise, mostly, however, looking at pacing during exercise in cool conditions. When we look at pacing in the heat, there are 2 main mechanisms that have been proposed to regulate effort. The first is the cardiovascular strain mechanism, and the second is the anticipatory regulation mechanism. Now, the cardiovascular strain mechanism proposes that an increase in thermal strain, which is mediated by an increase in both core and skin temperature, decreases oxygen uptake. So as thermal strain increases, so does cardiovascular strain, which ultimately decreases oxygen uptake, and therefore as a result of impairing sustainable as well as peak power output, as we saw in the previous figures. The other mechanism states that muscle recruitment is adjusted, or more so downregulated in anticipation based on the rate of heat storage in order to prevent thermal injury. So as the rate of heat storage increases during the onset of exercise, or at the onset of exercise, power output eventually decreases so that thermal injury or heat stroke or heat stress don't develop. However, throughout this presentation, I'd like to try and demonstrate that the decrease in VO2 max is the primary determinant influencing self-paced exercise in the heat. Now, if we go back to the origins of the cardiovascular strain mechanism, it comes from a redistribution of blood, so circulatory changes. So when we exercise or even walking in cool conditions, we can see that central blood volume is quite well maintained, whereas in the heat, a lot of the blood is redistributed to the skin or the periphery. So obviously skin blood flow and volume increases, as does heart rate to maintain cardiac output. And one of the mechanisms that help with redistribution of blood is vasoconstriction in some of the internal organs, so the splenic and renal blood flow decrease. But regardless of that, central venous pressure, as you can see here, 5 and lower than 2 here, they decrease, as does central blood volume, stroke volume, as well as arterial blood pressure. Now, this redistribution of blood has the consequence of obviously increasing cardiovascular strain, which reduces VO2 max in response to a decrease in maximum cardiac output. So if we look here at a ramp test to exhaustion in cool and hot conditions, we can see that cardiac output in cool conditions is 22 liters per minute, but decreases to just above 18 in the heat. And this is at a heart rate, maximum heart rate of 195 in both conditions. But because of the significant redistribution of blood to the skin, stroke volume is influenced, is much lower in the hot than the cool condition. As a result, cardiac output is decreased, and therefore VO2 max, which in the cool increases to 3.8 liters per minute, is decreased to 3 liters per minute in the heat. So what this does is that it increases the relative exercise intensity for a given absolute work rate. So for example, if the subject or the athlete in the cool condition is exercising at 2.5 liters per minute, so for example 250 watts, they'll be exercising at 66% of their VO2 max. However, in the heat, at the same power output and absolute intensity, they'll be exercising 83% of their maximum of VO2 max, because VO2 max has decreased from 3.8 to 3. And this is a bit of a linear relationship. If you look at differences or different ambient conditions, as the ambient conditions increase, VO2 max decreases, and so does performance time during a concentrate exercise. As Professor Saka alluded to, the core-to-skin temperature gradient is also very important in this relationship. And with the core temperature-to-skin gradient, we can estimate skin blood flow requirements. And if we look here at relatively even core temperature of 38 or 39 degrees, as skin temperature increases, the core-to-skin temperature gradient narrows. And as it comes down to 2 degrees, for example, the estimated skin blood flow requirements are 4.4 liters per minute. So naturally, this narrowing of the gradient increases the skin blood flow requirements. And a good example is this, this figure from Raoul in 1974, where we can see a rapid increase in skin temperature, causing an increase in core temperature, heart rate, and cardiac output. However, a decrease in central blood volume, stroke volume, as well as mean arterial pressure. And it's these adjustments that are suggested to mediate self-paced exercise performance in the heat via the reduction in VO2 max. Now, we did a study in 2011 looking at self-paced exercise for 40 kilometers. And as you can see here, power output was maintained relatively well in cool conditions. We see the end spurt, whereas in the heat, after about 15 minutes or so, power output started decreasing. And this was in conjunction with, obviously, a higher core temperature, high skin temperature from the onset, which obviously narrowed the core-to-skin temperature gradient, resulting in almost a twofold increase in skin blood flow in the hot trial. Now, in conjunction with that, we had obviously a very high cardiovascular strain. So even though power output was lower in the heat, heart rate was higher by about 8 beats per minute. And during the final end spurt here, where we had the subjects go at maximal effort, we measured VO2 peak. Heart rate in the heat was 100% of maximum, whereas in cool conditions was 98. Throughout, we saw that stroke volume decreased, as did cardiac output, as did mean arterial pressure. And what's interesting to note here is that even though heart rate increased to maximum here, because stroke volume couldn't increase, cardiac output didn't increase in the hot condition as well. As a consequence of that, VO2 was held constantly throughout, as was similar to power output throughout the cool conditions, and then increased at the end, but in the heat was decreased and then could not increase as high in the hot condition as in the cool condition. And before the trials, we had done a preliminary VO2 max in cool conditions. And what we did here is we compared, obviously, the decrease in VO2 max or VO2 peak at the end of the time trial in cool conditions, which was 5%, whereas in the heat, it decreased by 23% compared to our preliminary VO2 max. So overall, a decrease in 18% after a 40-kilometer time trial. So therefore, this led us to conclude that the rise in thermal strain leads to an increase in cardiovascular strain and obviously a progressive decrease in VO2 peak. And this progressively increases exercise intensity throughout. So it's not the case that VO2 peak decreases by a certain amount, but it's progressive. That's why the decrease in power output also is reduced, as well as peak power output. Now, recently, we did another study that we've just submitted, where we had the subject cycle for 750 kilojoules, and we saw a similar response in terms of power output, Similar starting power output, a decrease in the heat. This was in conjunction with elevated heart rate, core and skin temperatures, skin blood flow, as well as mean arterial pressure. And in this study, we measured mean cerebral artery, or mean blood velocity, which is an index of cerebral blood flow. And we saw that despite the increase or the higher thermal and cardiovascular strain in the heat, cerebral blood flow was maintained similarly in both conditions. Although it tended to be higher in the cool conditions, this was not significant. And we attributed the similar response in cerebral blood flow to the maintenance of a similar relative exercise intensity during the time trial, which allowed for comparable hyperventilation-induced PaCO2 because cerebral blood flow is driven by changes in arterial pressure of CO2. And this was, we observed also a similar respiratory frequency as well as ventilation. So if we want to apply some of the mechanisms, I guess, for pacing in hot conditions, we need to take a step back and look at pacing in cool conditions. And normally, trained, experienced, and motivated athletes have an even pace or adopt an even pace during time trial in cool conditions. But really, it looks more like a variable pace. So they start off a bit higher than what they can maintain, then they settle into a rhythm, and then they do that final end spurt when they see that finish line, in labs anyways. So this obviously requires balancing the relative contributions of both aerobic and anaerobic metabolism to sustain effort at that kind of physiological limit or fatigue threshold. And this has also been termed critical power, so the power output that someone can sustain for a given effort, or performance VO2, which is the percentage of VO2 max, again, that someone can sustain for a given effort. And that given effort is quite important because, again, what you can sustain for 15 minutes might not be what you can sustain for 2 hours. And obviously, accelerations and decelerations increase energy requirements. So if you were to adopt this pacing strategy, then go really hard for a bit longer, then you'd have to recover and come back to your even pacing strategy. So you want to avoid, obviously, accelerations and decelerations, which in the lab is much easier to do. But if you're outside and there's hills and things of that nature, it's a bit more difficult. So if we come now to pacing in the heat, well, it's well established that high core and skin temperatures induce large reductions in VO2 max in the heat. However, VO2 max is usually maintained at the onset of exercise for 10 or 15 minutes because as the core to skin temperature gradient narrows, as skin temperature or as core temperature increases, that's when the reductions in VO2 max occur. So for the first part of exercise, you can mostly maintain your VO2 max as well as some of the vasoconstriction that occurs at the onset of exercise. Therefore, critical power appears to be adopted at the onset of exercise or self-paced exercise in both hot and cool conditions. So if you look at different studies from Tatterson and colleagues in 2000, you can see for the first 5-10 minutes, power output is similar. Again, with the Tucker study, for the first maybe 40%, power output is similar in hot and cool conditions. Our study here, another study with 40 kilometers, and then our last study here. So again, power output is similar at the onset of exercise in both hot and cool conditions. However, as thermal strain progressively develops, so does cardiovascular strain. So consequently, power output or running speed decrease in the heat in order to maintain that relative intensity associated with critical power. So this critical power concept in the heat may be viewed more so like a critical intensity that we maintain. And for example, it could be 85%. Now, it's not specifically one, it's more of a range, but it's not like 85% and that's it for everybody, or even for an individual, but it's more of a range in which someone can exercise or maintain a pace. And this has been observed not only in the lab, but again, during running. And as Dr. Nebo alluded to today, with exercising in the heat in the field, you can see that cool conditions, the time trial is here, but after 2 days in the heat, athletes start their time trial at the same temperature. So then you think that maybe, okay, they spent 2 days in the heat and then they time trialed like this and they had a significant decrease in power output. So maybe next time they'll start a bit lower in pace. But no, the next time they still had a drop, not as significant, but they also started at the same intensity or same power output. Now, if we look at the anticipatory regulation mechanism, this, I guess the origin of the mechanism stems from a paper from Ulmer in '96 where they looked at, they proposed an ability to feed back the intensity of muscular work to a control system via metabolic afferent feedback, so a bit of a closed loop system. And then after that, Noakes and St. Clair Gibson developed the central governor model, which I'm sure many people have heard of, where exercise is controlled through active neural calculations by the brain, both consciously and subconsciously. And basically, the brain evaluates these internal sensory information and produces an exercise intensity that will allow homeostasis to be maintained. So based on this premise, Tucker and al. did a study. Again, they looked at 20 kilometers cycling in the heat, and obviously power output started to decrease after about 40 or 50%, and was only significant in the last 20%. But they said that anticipatory downregulation of power output occurred during the first 6 kilometers of the time trial. What's interesting to note here is that core temperature, heart rate, and RPE were similar between the conditions. However, what was different is the skin temperature at the onset of exercise, which was about 7 degrees higher in the heat, and by the 5 kilometer mark, the core to skin temperature gradient had decreased or narrowed to 2 degrees, which naturally would increase skin blood flow requirements for heat dissipation. In a follow-up study, they looked at clamping RPE, so rate of perceived exertion, at 16. So the subjects had to exercise until exhaustion, so until they dropped under a certain power output, maintaining an RPE of 16, so they could decrease their power output without knowing by how much they decreased it. And as you can see, power output decreased much more significantly in the heat, 2.35 watts per minute, compared to normal and cool conditions. So therefore, they suggested that exercise intensity is controlled by initial afferent feedback regarding increases in skin temperature as well as the rate of heat storage. And you can see here that the rate of heat storage in hot condition was obviously positive and high, whereas in normal and cool conditions it was quite low. It's actually negative 80 kilojoules per minute. Therefore, they further suggested that this feed-forward anticipatory strategy served to defend thermal homeostasis, and that this was based on RPE as a mediator. What's interesting to note, however, is that for the first 50% of exercise in the heat, power output was higher than in normal and cool conditions by about 20 watts. Although this was not significantly different, it's still an increase in 20 watts for the first 50%. Now, there is a bit of contention regarding this mechanism, and I think someone with Nick, I think, will be presenting on this a bit later on. But Dr. Ollie J went back and looked at the calculations on which the rate of heat storage was based, and he noted that because of these rapid changes in skin temperature, especially in the cool, that evidence for this anticipatory feed-forward mechanism was fundamentally flawed, suggesting that there was no feed-forward mechanism associated with the rate of heat storage. And another important point, as I just noted, there was a 20-watt increase in power out or higher power output in the heat when exercise started. But if the anticipatory mechanism was truly a feed-forward mechanism, then it should act before external disturbances have a chance to influence it, because after that it becomes a feedback mechanism. So power output in time trials in the heat should start at a lower power output if this was a feed-forward mechanism. So again, core temperature after about 40% was above 38, and with skin being so much elevated at the beginning, this would increase the skin blood flow requirements. We saw an elevated heart rate in the heat, so naturally there was some circulatory and cardiovascular strain associated with exercise there. Others have also demonstrated or suggested that heat-related decrements in aerobic performance don't occur because of modifications from pacing at the onset of exercise, but rather from an inability to maintain the initial pace during exercise. And this was during modest elevations in core temperature, but a high skin temperature. It's also been shown that high skin temperatures by themselves without hyperthermia do not affect self-selection and modulation of self-paced exercise or cycling, but this was only for 7.5 kilometer cycling, which would be over in 15-20 minutes at the most. Also, higher skin temperatures appear to reduce overall performance, but not pacing pattern. And what's interesting to note here, however, is before heat was applied, power output was already lower from the onset of exercise. So in summary, self-paced exercise is clearly influenced by internal, external factors. So there's many aspects that influence it, especially because it's a behavioral response. So knowledge of the task, motivation, fitness level, experience of the athlete, environmental conditions, as well as neural feedback. However, it appears that the progressive development of cardiovascular strain, which leads to a decrease in VO2 peak represents the primary determinant impairing performance in the heat. And this appears to be to maintain a critical intensity. So as power output decreases, I would suggest that relative intensity is maintained because of the decrease in VO2 max. And finally, naturally, the central nervous system plays a role in modulating performance, but it's through conscious behavioral adjustments in effort to modify pacing in order to maintain that relative intensity. Thank you very much.
All right, thanks, Julien. Any questions on this one?
I think it's getting late. I saw a few people kind of nodding off there.
Well, I've thought of a couple. One is, has anyone done any work to determine like the ideal pacing strategy, whether it be in cool and or in heat, and are they different? Are there data on that sort of thing?
Well, there's many. I think I'm not sure if Bart's here, but he's done a review recently with pacing. I mean, there's a lot of pacing articles out there. I'm not sure if they all agree with each other, but I think ideal pacing strategy varies based on the task or the length of the exercise, and appears based on, well, my view anyway, is that it's based on a critical intensity or that critical power which you maintain for a given effort. So the critical power concept comes from what power you can maintain for an hour. And based on that, there are calculations you can make to determine, okay, well, what power based on this can I have for 2 hours or for half an hour and things like that nature, in cool conditions anyways.
Thanks very much. I just want to ask if, in fact, this is from Ron Mon. He once shared with me, say that is it true that in actual race, everyone self-pace is actually the front guy or the pacer doing the regulation, and the rest are just being forced to maintain that pace? So is it true that in real live competition is self-regulation for all?
That's a very good question, because here we're talking about, first of all, laboratory tests where someone says, we say go and you finish there, or time trials as we did in the heat. And as I think you guys did as well on a track where the person is just asked to self-pace. So a time trial in cycling is like that. But your point is that, you know, when you have a mass participation run, what pace do we follow? And that's a good question, because I think that would definitely change depending on, again, your goals. If you say, okay, I'm going to stick with this guy today, then you might not adopt your own pacing strategy. So you might start faster, but then at some point you might pay for that and slow down. Or you might say, okay, I've been burned by this guy a few times, so I'm going to start at my own pace and see what happens. So that's a very good point. And that's one aspect that hasn't really been looked at in these studies, because it changes based on your goals, you know, who you run with and things like that in nature. So that's a very important point.
Well, thank you for a nice presentation. Now you say, I have to defend, because we used really much time in writing this review where we said that it was integrated from different. You say that it's mainly the cardiovascular and the reduction in VO2 max, but couldn't that depend, because all the time trials that you showed here is in the range from 1 hour and down to so very intense. Because I would say that the observation that Bart had, Roland, where they gave the drug was that. And that was like 1 hour and then half an hour or even 40-minute time trial. There they saw that when they gave the Ritalin, which was the dopamine reuptake inhibitor, that they actually exercised with a higher heart rate. So indicating that in the more prolonged the trial becomes, the more submaximal the intensity comes, the more other factors will influence the pacing besides from the cardiovascular.
Yeah, I agree, and that's why obviously I tried to mention that it was multifactorial, but regardless of the pacing, you could still see that there was a decrease between 30 degrees and 18 degrees. And the other thing, as I mentioned, that, you know, it's not necessarily a specific critical intensity or critical power. It's obviously a range there, and as Bart mentioned, there might be some sort of reserve. So if you give someone drugs, they might, you know, exercise at the top end of that kind of range rather than in the middle or at the bottom of that range, what they can maintain, So I think there is a range. I think, again, the primary determinant is the decrease in VO2 max, because you see it with 18 and 30 degrees. But again, there is a range that you can maintain, and then maybe some variations within that range based on pharmacological manipulation.
Quick one. Oh, that's right, I'll pass it. You know, I think the idea, and John's going to talk about some of the work done at Georgia that I think lays this relative intensity, supports it. But
The question is how do you sense relative intensity? Okay, and we've talked about that, Lars, and that's a good question. And I think that, at least in my mind, getting insight is some of the hemorrhage data stuff that Vic Convertino's done is really parallel to working in the heat. And what he sees with hemorrhage is similar in the heat, is that your blood pressure is maintained, and it gives out. But when he goes and he actually, even if blood pressure is maintained, which it is in the heat, or sometimes it might drop slowly, but then it gives out, is what he found is when you look at the aortic pressure curves, that there's a lot of changes in that aortic pressure curve that when you start looking at that's going on, and you could sense that the cardiovascular system's struggling for whatever reasons. And I wonder if it's that instability, you know, sensed by the baroreceptors, by these fluctuations, pulsatile fluctuations, it's what's maybe even providing that feed-forward mechanism.
Possibly, yeah, that's an interesting point. Thanks very much, Julien. We'll leave it here.
Okay. Thanks very much, Julien, again.